So, now that we've seen how automatic machine learning works, let's get to another question, which is, which features are important? This is a question that we often have. So there's a bunch of things that we can measure. Some of them are easy or cheap. Some of them might be expensive. Not like we might do blood work on people. So it's natural to then ask for the machine learning task that we solve, how important is each feature? So we'll be talking about model interpretation. We made predictions with the black box model. And like for all practical purposes, AutoScaler is a black box model. So how can we know how important each feature is? Well, let's briefly review where we're headed. There's two ways of solving that problem. Either we choose a model that is so simple that we can understand everything, which we can say is intrinsic interpretation. Or alternatively, we can fit a complicated model and talk about post hoc interpretation, which is we have this model now, how good is it? Or like which features are helpful for it? So specifically, when we talk about post hoc interpretation, we'll talk about feature importance using so-called Shapley values, and we'll get to what that means. Then we'll have a quick crash course in Shapley values, and then it's your turn. So let's briefly talk about the taxonomy. We can have intrinsic understanding of the importance. If we are after model interpretation, we can choose a model that is intrinsically interpretable, for example, linear regression. Here we have linear regression. Now, like the estimate that we have about y is a constant beta 0 plus a constant beta 1 multiplied with the first feature value x1 plus and so on and so forth. In that case, we can interpret what beta 1 does. We can say, well, what is it that it's interpretable? Well, we can know exactly what happens, which is if beta 1 is larger, it means that x1 has a bigger influence on our predictions. We can say what we really measure is if we increase x1 by 1 unit, the estimate of y will increase by beta 1, holding all other x constants. Now that assumes that we always have all the other x and that they don't change. We just make one of them bigger. But in that sense, we can interpret the betas as feature importances. And it's very transparent to understand that. At the same time, if we have many parameters, it's hard to interpret how they come together. Now, I also want to mention that basically, if we are in a high dimensional space, that joint space of x1, x2, and so forth can have complex properties. But the second issue is that it might give a bad fit to data. So linear models are nice until the data has highly nonlinear properties. And then we need to ask, is this the best fit for our goal? So let's instead talk about post hoc techniques. If we train a black box model, or we're handed a black box model, we engage in post hoc interpretation. We have the model, and then we want to ask, well, what makes this model work? We need to consider the layer of the data science process. There's a lot of aspects that go into it. With ad hoc methods, we step further away from the data in the world, so we need to take them all with a grain of salt. We need to be careful about that. So here's one way of thinking about it. We have the world. The world is expressed by data. It is modeled as some kind of a black box model. And then we try and use interpretability models to explain to us how the black box model works, and then hopefully we as humans can understand it. So here's the idea of Shapley values. We want feature important. How much does a feature X contribute to our model's predictions? There's a popular solution from game theory, which is Shapley values. It's originally meant to deal with basically how much credit assign to people. Shapley answers the question as follows. If we have players, in this case the features are the players, that contribute to some output, in this case it's model prediction, how much credit or importance should each player receive? So here's an idea. We have 3 farmers, A, B, and C. Jointly those 3 farmers produce 9 bushels of wheat. What we want to look at is compute the marginal contribution of each farmer, which is what does this one farmer add to what the group does. So we have Alice, Bob, and Celine, they're farmers. They have 9 bushels of wheat together when working together. How do we assign how much credit everyone receives? So here's an idea. Let's say we have farmer A, which produces 5 bushels. Her marginal contribution is 5. If we go from 0 to only Alice, we get 5. Now we can say we add an extra farmer, Bob. Bob's marginal contribution is 1, and now we have 6 bushels. And then we add Celine. Celine harvests 3 of them, so her marginal contribution is 3. But of course, in this case, we started with Alice. The results could have been different if we had started with Bob, or if we had started with Celine. So what we can do for Shapley values, we order them in every possible order, and we can then always ask, okay, what does C add over AB? What does B add over A? What does A add over nothing? Similarly for each of the 6 different permutations of that. So we compute everyone's marginal contributions over all possible combinations, and then we take the mean, and that's what we call a Shapley value. Back to model interpretation. Now the farmer is what we call about features here. So instead of marginal wheat contribution, we call about marginal feature contribution to predictions. Instead of total bushels of wheat, it's overall model predictions. So the Shapley value of a feature in a model is the average marginal contribution of that feature to the model predictions. Does this seem like a good feature importance measure? Well, there's some people that are very happy about Shapley values, and some people are less excited about it. And how does this compare to linear regression coefficients? Now, it's solving a very different problem. It's asking, in this overall nonlinear interesting setting, what are the marginal contributions of the feature? Now it's your turn. Thankfully, we don't have to compute Shapley values by hand. The Shap package allows us to plug and play Shapley value importance right into our notebooks. Your turn to try.